So, by way of introduction, one tries to delve into, let's say, I would say, foundations of quantum physics. Okay. Nowadays, it is very difficult, impossible, I would say, to avoid reasonable knowledge of GNS construction, which I tried to give last time. I will come back to it. And this result, this theorem, which goes by the Tomita-Takisaki theorem. Okay. This, I will talk about what this is in this lecture in finite dimensions. So you know all the steps involved in the calculation. So why is it important? It is important because, for example, if one takes the vacuum and expectation values of local observables in vacuum, okay, it turns out that this is not a pure state. Okay. It is pure if you take the entire algebra on space-time, you take creation, annihilation, operators, and so on. It is a pure state. But when you start looking at local algebras, it is not pure. Okay. So the Tomita-Takisaki theorem is a canonical way of purification in the quantum information language. Okay.
Purity or not is a property of the state or the algebra?
The purity, it is a property of the state. Okay. So purity, how is it defined? GNS, so the GNS construction is intimately linked to the Tomita-Takisaki theory. So how do you define purity? One takes the state, whatever you are taking, you take expectation values of observables. Okay? And by the GNS construction, you get a representation of these observables on a Hilbert space. Okay? The question is that representation irreducible or reducible? Okay? If it is irreducible, it is a pure state. Then the corresponding density matrix you construct from the JNS vacuum, what we label by the unit vector, is a projection operator which gives the zero entropy. Whereas if you have when you do the reduction, it is no longer an irreducible representation. You will find that it is a convex combination of different density matrices, and that gives rise to an entropy. So purity and impurity are directly linked to the properties of the state of the algebra. And in the lecture last time, when I did 2 by 2 matrices, we got for the state I wrote down as omega and lambda, we got 2 irreducible representations. So that state was not pure. It was a mixed state, and you can compute its entropy. Okay. So you can ask, is that a purification of the state? Okay. The quantum information people are very much interested in thinking of this mixed state as coming from a pure state by restricting the algebra of observables. Okay. Is there such a purification here? And the Tomita-Takisaki theory is a canonical purification. And we will see that it has many important properties which directly impact on quantum field theory and quantum theory in general. Okay. There is a much more elaborated theory of purification, which is not very much used by us, by physicists, but it's very much used in mathematics, called the Stein-Spring. There's a theorem associated with Stein-Spring. Okay. I will not talk about it. Okay. It does play an important role on the math side, but we will not talk about it. Okay. And we will see that this purification has very nice properties, and it is sufficiently simple. At least the content of it is sufficiently simple that we can check it in finite dimensions. Okay. Of course, when you go to infinite dimensions, new things start happening. So this is by way of general introduction. Okay. By way of story, okay, Okay. Why? What is the history of this thing? The history of this Tomita Takesaki theory is itself interesting. Tomita wrote appeared this paper in Japanese, okay, and in the 70s, I think, and not a single soul understood what he had written except Taketani. So the story goes that Taketani, not Taketani, Takesaki. So Takesaki is interpreted, he rewrote the whole paper in English, okay, and presented it in some meeting in the US, okay, where a similar result was obtained by, what's their name? Haag, Hugginghouse, and Winnick. Haag, Hugginghouse, and Winnick. They had done a similar analysis. In fact, it was the same analysis done in the context of finite temperature states, and they realized that they were doing the same thing at that time. So it is Takesaki who made this Tomita Takesaki theorem to available to the general public. Okay. I don't know what happened to Tomita. He disappeared. I don't know of what his later publications are. He must have. Maybe he did not know English and ceased writing. I have no idea. But this is the history. And our friend Haag Guggenholz and Winnick paper, Haag talks about it in his book on local quantum field theory. Okay? So, what is this theorem? Let me tell you. So, what is the theorem? So, let me.
So, what is the purification? Like this character of the state came from the fact that the observables were local.
That observables are local, you get mixed characteristics.
Right. So when you purify, what are you? So you are no more looking at local observables.
The purification, what it happens, the remarkable thing in quantum field theory, which I will talk later, the purification is obtained by taking some tensor product of the original Hilbert space with another one, okay? And the purified state consists of a pair, which I write down in the finite dimensional case. And in quantum field theory, what happens is that the other one is associated to the causal complement of the original local observables. So the big remarkable discovery, I would say, by Wickman and Bisonino and Wickman was they did this thing without knowing Tomita Takesaki, and they found that this commutant was actually the causal commutant. That was a very remarkable theorem. Why did it happen? And it was also independently discovered historically in the study of thermal states by Umezawa. They all coincide. So some historical coincidence was happening at that time. People coming to it from different angles. Okay? And we will be going into this Umezawa activity. And in the coming lecture, I will present to you what Bisonino and Wickman did and show that naturally you get thermal states. Okay? So we will proceed in that direction. Sorry.
Is there an assumption that you're looking at the non-affected?
No.
When you say that you're localized, you're specializing your local algebra, then you have a mixed state.
That is a general theory. So the vacuum that.
So I could have say compact set. I not call that a local algebra. The algebra of this compact set is not for.
So the answer is I don't know. If you take all operators on say 3+1 space-time, all operators in three-dimensional slice. Okay, so all operators in 3+1 space-time. That algebra, vacuum state on that algebra is pure. No, if you take R3 and say I don't want R3, you compactify it, what happens? I don't know the general answer. I would imagine that this kind of problem may not arise, but I am not sure.
Can you tell what this causal complement is? Because that apparently that is what compensates for the local character. I'm not taking
Causal complement is simply you have the fields. You take the, I will write all the equations as we keep going, but it's okay. Take the quantum fields and smear it with test functions in a compact region. Compact means closed and bounded region. Okay? That region generally is stated to be what people call causally complete. Causally complete means you take space-time region, take the causal complement of that, all things which are space-like, and take a complement. That is, take some region O prime, O double prime. Okay? O double prime will contain O, but it may be slightly larger. Okay? So O double prime is a causal completion, and it is also, if you permit it, is also normally hyperbolic, what is it called? Uh, globally hyperbolic. Okay? So it can actually like a space-time. If you smear with test functions supported there, a quantum field, that will be a causal, that will be one of my local causal algebras. There is the issue of exponentiating it, we'll come to that. And take the causal complement, and that will be the algebra of fields smeared in O prime, the causal complement, and they will commute. Okay. So we will see that localization here does not mean bound localization. There is no projection operator whatsoever to local region. We will prove that it doesn't exist. So I will prove in the next lecture that what we are taught in non-relativistic quantum mechanics about Bond's interpretation of observations, the quantum field theory context is simply wrong. It doesn't exist. Okay? You violate all kinds of things and get contradictory results. So we'll come to that. We are all patient. I'll come to that and show all the equations. Okay? So why it is happening? That is rather simple to show. It's coming from the fact that the Hamiltonian is bounded below. Okay? So we'll come to that as we proceed. Yes. So I want to show how this whole thing arises. So I want to do it in finite dimensions. So let me take the algebra of observables. So I define my algebra of observables to be all n cross n matrices for complex numbers. Okay? So it will be some say n qubits. Okay? Well, n cross n. So enough qubits, n over 2 qubit. Yeah, not even enough direct sum of, I mean, several qubits, so that the entire dimension of the Hilbert space adds up to n. So I take n by n matrices, and I take a density matrix rho on this n by n matrices. The thing I want to do is to consider those density matrices which are non-singular. Okay. So this is the issue. This is the thing we have to focus on, the fact that it is non-singular. Okay. Because of non-singularity, we will see that this rho on this algebra is not pure. It is mixed. Huh?
That's like saying it is right.
It's obvious to you. Good. Why?
If it's pure, then it doesn't become complex. Because that has to have a lot of zero.
Not no. Yeah. Oh, you're going the other way. Yeah. Here I am taking n by n matrices with all non-zero eigenvalues.
No, you're talking about rho.
Rho is non-singular.
So when you say rho is non-singular, it doesn't have zero eigenvalue.
Yes.
But if it has zero eigenvalue, then it is.
There will definitely be other, yes. So that's why I said you are going the other way around. That's fine. So I want to consider the case where rho has no zero eigenvalue. This is a kind of situation. I urge you to study basic group theory. If you study group representations of compact or finite groups, first few pages you will come across this business of regular representation, left and regular, right regular representations. This is the same. There also you have a similar theorem that every irreducible occurs as many times as the dimension of the irreducible for these groups. Okay? Very easy to prove, and a similar result is going to happen there. So the left regular representation defines a state on the algebra of the group you are considering, and that is not pure. Okay? In fact, this is a starting point, if you like, for this whole game due to Naimark. Okay? I think Naimark was the one who started this whole thing, then joined with Gelfand. Okay, how does it happen? So since I am given the fact that rho is non-singular, and of course it's a some n by n matrix, so I can make a polar decomposition of this. I can make a spectral decomposition of rho, which is what I have done here. I'm making a spectral decomposition here, where Fi's are normalized vectors. The basis of my Hilbert space is I take to be orthonormal, and this AI squared they will be non-zero because rho is non-singular, and they should come to one because trace of rho is one. So this is the spectral decomposition of rho. So just as an exercise, let me just check that this rho has no null states in the GNS construction. In the GNS construction, if I take any two vectors, okay, so for example, I take any two vectors m and m, the scalar product of the two m's is given to rho by taking rho and taking n star. Okay. This is the GNS construction of which gives the scalar product becomes the rho. Okay. Let me work it out, and let me write it down into, and you get this equation. So I'm taking the trace of this object with regard to the rho which was written here. So the AI squared times this equation. And that is, suppose there were a null state, it will be 0. Okay. So this is null, I'll get this expression 0. So this will be 0. But AI squared are positive. So each term should be 0. Okay. So if each term is 0, it says m acting on Fi is 0. But this is the scalar product. Okay. If m acting on Fi is 0 and Fi is a basis, as I showed it there, we can conclude that m is annihilating all basis vectors, so m is 0. Okay. So we see immediately that this rho I have written down has no null vectors. So the condition that rho is not zero is the same as the same statement that rho is not zero. Now, there are two words which you will keep hearing in this whole game. One is a vector is cyclic. The other phrase you will keep hearing is the vector is separated. So what does cyclic mean? You take the vector and add to the full algebra. The issue is whether I get the full Hilbert space. Okay? If you get the full Hilbert space by acting on the vacuum, the state the vector state you are starting from, by the operator model, do you get all the vectors? If you do get it, then that vector is separated, is cyclic. Okay? This is the language people use. Separating means that if an operator annihilates one, that operator is 0. Okay? So the only operator which can annihilate 1 is 0. So why is it separating? Because any two operators which differ from each other, their difference cannot annihilate this vector I have chosen. Okay? So a vector like 1, the question is it separating, cyclic and separating? So if cyclic and separating, you will see immediately that this state is not pure. And the rho I have written down has that will be both cyclic and it is separating. So we will see how it will go.
So this one is the vector is a Hilbert space associated to this as local algebra.
This local algebra, m by n matrices, so you remember that the states are labeled by matrices. So this m by n matrices have unity in the algebra. So this is the vector I get by labeling it with 1. So that is a cyclic and separate. The vacuum sector, for example, the vacuum vector in quantum field theory for all of space-time is both cyclic and separating, but not for the local algebras. So it is turns out to be cyclic for the local algebras, but not separated. So that is what causes this Dissonant-Wickman theorem on causality, and how CPT comes into the play. It is cyclic and separating. I didn't say no, it will be highly impure. We'll see. Immediately. It will be the worst possible case you can imagine. We'll see how it happens.
Can you repeat the definition?
Sorry?
Can you repeat the definition of cyclic?
Cyclic is simply means you start with the GNS construction or any construction, you start from some vector. For example, in quantum field theory, you start with the vacuum and you take creation annihilation operators. In the local algebra also, you can start with the vacuum. Consider the full algebra, say for example, local algebra acting on the vacuum. You get a set of vectors in Hilbert space. It's infinite dimensional. If you are very fussy, take its completion in the norm. There is some subspace of the Hilbert space. Are you getting all vectors to the Hilbert space? If it is that vector you started from is cyclic. Separating means what I told you, that no two operators of the algebra which are different, their difference can annihilate the starting vector you are starting from. Okay. Here, for example, the difference of two matrices which are different should not annihilate one. That's not so obvious because take this one and take m1 minus m2 acting on one, I get the vector labeled by m1 minus m2, and this norm is not zero by the definition I given. Okay. So norm is not, so it's not a zero vector in the JNS construction. So this is certainly separating. Okay. What is it cyclic? Do I get all vectors starting from one? In this language, it is sort of obvious because any arbitrary matrix acting on this will give me a vector in this n by n space. Okay? So it looks obvious, but I want to write this equation in a slightly different way using Umesawa's principle, which is both convenient and based upon what I was telling you last time. Okay?
Just to clarify, the vacuum of local algebra is not certain.
Which one?
The vacuum space.
Vacuum. No, it is cyclic and separating. Okay?
For local algebra.
For local is no two. If you take all operators on R3, okay, the vacuum is not separating. Why? Because of the fact that the annihilation operator annihilates the vacuum. Annihilation operator is not a zero operator. It annihilates the vacuum. So the vacuum has a non-trivial vector in your algebra which annihilates the vacuum, the starting state.
But the addition operator is not part of the
in all of space time. So if you don't like the fact that I am dealing with annihilation operator, you can take this, let's say, take the number operator, exponential I times a dagger a. Take the number operator. Okay. The number operator has a spectrum which is what is it? Exponential I, exponential 2i, 3i, and so on. Okay. So take exponential I times a dagger a minus 1. Both are boundary operators. Okay. I think that is what is bothering you. Identity is in algebra, is a boundary operator. So if you take all, for the local algebras, these vectors are cyclic and separating. If I said it like that, it's wrong. But in quantum field theory, but cyclic, no, for local algebras, the vacuum vector is cyclic and separating. For the algebras are all of space-time, which is not separating, because I give you an example. So what is the operators on all of algebra? Take all bounded operators. Some people have questions on what is bounded, we can argue about it. Take the number operator n and take exponential I times n. It's a phase. Okay? And it has an eigenvalue which is 1, okay? Where n is 0. Okay? So the vacuum vector. So take that thing and take minus 1. So take exponential I n minus 1. It annihilates the vacuum. So, but exponential I n and 1 are different operators. Okay? And it is annihilating the vacuum. So the vacuum is not separating in the infinite algebra. And because of this loss of separability, you do not get this multiplicity of you don't get impure states. Impure states is buried in this fact that the vector is cyclically separate. Okay? And that is the observation. And we already knew that actually. If you had studied group, as I keep referring back to group theory, finite groups or character theory, it's already there. If you study it more attentively, it's also useful to do calculations. You see that the result is already there. And it is coming up here. There is a small lemma or theorem or whatever it is, which I have not written. And you can take it either as an exercise or whatever, or I can prepare some slide. The thing is that if you have a algebra and you take a vector which is cyclic is separating, there is a certain duality. So M is my algebra of all n crossing matrices. Okay. Take M prime, all matrices which commute with them. Okay. Then the result M is that if a vector is cyclic for M, it is separating for M prime. And if it is separating for M, it is cyclic for M prime. Okay? So the moment I tell you that the one vector 1 in this n by n matrices is cyclic and separating for n cross n matrices, it is also cyclic and separating for M prime, the algebra which commute with M in this Hilbert space. Okay? This Hilbert space, remember, is n cross n dimensional. Okay? So what is this M prime? This, well, you can think of it nicely the following way. That n cross n matrices act on the left of the vectors standing in the argument, and the commutant acts on the right of this M by n matrices, and they obviously commute. This is what happens here. Okay? In the general case of quantum field theory, it is more complicated, but this is the mechanism. Okay? In group theory, it's definitely the left and right regular representations, and they commute. That is what they call this group theory. I want to write the state rho I have written down, which is given by this expression in terms of the double Hilbert space, a purification. And I told you what this thing is due to Umezawa. At least the first time I saw this was in Umezawa's statement of thermal field theory. Some of you may know it. He writes the thermal state in terms of an extra Hilbert space, right? And doing some activity with that. And that is what we are doing here. There are some questions. Yeah. So what is the trick here? So I take this, I want to write this trace of rho m in terms of a new vector state, omega, which is a purified state. There is no density matrix. It's a vector in some Hilbert space. And what is it? What Umezawa did was to double the Hilbert space. Phi is an n-dimensional Hilbert space for which it shows a basis. And Gi is another orthonormal basis in a new Hilbert space, which I call K. And you take this vector. AI of AI was the coefficient which appeared in the definition of rho. So I look at this vector only, this combination, and I define that to be the inducing cyclic vector, inducing vector for the representation. This is clearly, I want to show that this is the pure state. So, well, it's a vector state. So, it's coming from a vector in some Hilbert space. So, this is the purification of my density matrix that Umezawa writes from. Does it give the right expectation value? Do I get trace of OM this means? The answer is quite obviously yes. Why? There are two things I have to prove. Okay? Let me first check that the expectation values are okay. Okay, let me go back here, and I want to show that if I take the expectation value of any matrix in this state, say any matrix M in this state, I get the right answer. So this matrices M I am writing on observables are acting in this double Hilbert space. Yeah. In this double Hilbert space, I allow my matrix. So both are n-dimensional, and I am allowing my matrices to act only on the F. They don't act on G. Okay. So the M's, the observables are now acting on half the vectors. And I want to consider, make sure that when I take expectation values, I get the trace of M before. But that is obvious because when I take the trace, this trace, the GI is cancelled out, okay, because nothing acts on them. So GI is 1, and two GIs are differing in index is 0. And since I am also coupling them with the same I, get AI squared. So you find that trace of OM is exactly AI squared summation on I. So this is what Umezawa did when he considered thermal field theory. And because he did like this, he could do calculations much more easily, and he can write propagators at finite temperatures and so on. Yeah. Even if when the dimension is infinite, you can do it. See, well, Umezawa does it. That book he has written, Umezawa in Kamefuchi, thermal double. This is the same as a thermal field double. Exactly the same. Okay. And yeah, you can do it. There's no, it's a particular purification, uh, which not, it is not unique. I'll come to that in a minute. Well, non-uniqueness is quite important. And the grand, uh, the grand unification, which is a Stein-Spring compression theorem, uh, is called compression. That much I don't know the origin of the language. Shows the most general purification. How to embed your GNS Hilbert space in a much bigger space, where the original mixed state becomes a pure state in the larger algebra with all the operators. And when you restrict the state to a subalgebra, you get back what is radical. It's called the Stein-Spring compression theorem. It is not, well, it's not a difficult theorem. There's not a lot of inequalities or anything like that. But you have to be patient on what is going on. Okay? Because it plays with operator theory a bit. Okay? But that is very commonly used by people doing fundamental algebras and other things. Okay? So this is a special case of that activity. Okay? This is enough for us because we will see that reasons which are not very clear, it appears to have a special role in quantum field theory. Why don't I use Stein-Spring? Okay? Apparently you can, but it doesn't seem to lead to any good results that I know. Okay?
So I thought the first is scheme only to the famous construction. Then what is the scheme that you are
K is an auxiliary Hilbert space, which the vector, cyclic and separating vector I am telling. So the cyclic and separating vector, with which I started, what happens is that if you do a GNS construction on that, you see that every irreducible representation of the algebra occurs as many times as the dimension. Okay. So we have a degeneracy of this Hilbert spaces. So you want to write, so it's a direct sum of several Hilbert spaces for the same irreducible. Okay. And you want it these Hilbert spaces as a tensor product. One for the algebra and one for the commutator. The commutator is acting on the degeneracy index, like I showed last time. So the commutator here will be acting on the GIS. So that freedom you want to, so this is so you're putting your algebra in a bigger algebra. So if you take all the operators acting on F and G, this is a pure state. Nothing, but if you act only on F, this is not a pure state because there is a degeneracy coming from G.
should I understand A as the same state, but with the commutator algebra?
With a commutator algebra, provided the state you are picking from is cyclic and separate. If it is not, then there are null states which you have to portion out. Then the structure will change. Okay? You can work it out, but it will change. Okay? And you may even get, if there are no null states, if it is not separate, I mean, this is large null state, you will find an irreducible representation. Then there is no degeneracy. So you may think of it, we wrote a paper that it is an emerging gauge symmetry. Okay? If you rotate the G's, nothing will happen. The observables are not affected by unitary transformation on the G's. So in our earlier papers and also here, what you are seeing here is an emergent gauge symmetry. It was not there, okay, but it emerges from the quantum theory. It's not something you put in there. That was the argument we are trying to suggest. Okay, so nothing will happen with G. So what I want to show, now is what Tomita Takesaki did. So I want to show that that this omega is cyclically separating. That is remember that cyclic means I have operators acting just on the right, left, this, and still I get all the vectors of the full Hilbert space. This is G cross K. Separating means that no two vectors, which are different, annihilate this vector. I want to show this. Then I will go to show how the so-called modular group emerges from here, you may ask what is the importance of this modular group. I will come. Yes. So the whole theory, the title is modular. Don't ask me where this modular came from, okay? But that is the language that is used by these people. And for structural results on the full algebra, especially in infinite dimensions, it seems essential. I did ask people like Sundar, why you want to have degeneracies of this kind? And he said that if you take irreducible representations, you lose information on the algebra. Okay? Some other things will go to zero and so on. Okay? So one needs the structure, he says, to understand the algebra in this depth. That is his statement. But
And complex, then you so of this algebra you could represent it. Am I right? You got reducible representation, which actually gives you H cross K.
no, this is not irreducible.
No, reducible,
Yes.
which is giving you H cross K, multiple copies of H, right? Now you're organizing it as H cross K and okay.
So this is the algebra to M cross M. Okay? M left cross M right. Okay? It will become irreducible. This is like a left regular representation and a right regular representation. Exactly. In group theory, which we use to find the characters of a finite group, things of this kind. Or to show that S3, that permutations on three objects, has two one-dimensional and one two-dimensional representation. This is a well-known fact. How do I know it? Well, this thing I told you about regular representations shows immediately that the sum of the squares of the dimensions of the irreducible representation is equal to the order of the group. Okay? That's a famous result, I think, due to Frobenius thing. So you see, S3 has one trivial representation, one totally antisymmetric representation, and one two-dimensional representation. Okay? So number theoretically, 1 plus 1 plus 4 is 6. So if you try to decompose 6 in the diaphragm, this kind of equation, A square plus B square plus C squared, equal to 6 A and B, C positive integers, you'll get the answer. Then you can go and hunt how to find this two-dimensional representation. It is not, well, for S3 it is trivial. But for to do the same thing for S4, S6, this equation gets more complicated. They give you some problems in number theory. Okay? So this is a thing like that here. Okay.
So you mentioned this G. We're talking about the asymmetry G. Like you can rotate your G basis. So it's only when you're thinking of operations on the input space X, right? Only
X cross K. I'm doing operations on X cross K.
But if you're going, so if the state changes,
the expectation values don't change because this G is cancelled out. So I meant any unitary transformation on G, when you take the expectation values, replace Gi by Ji prime, make it cancel out.
only transformations like identity times.
No, I told you on the left. My algebra is here on the left. So the observables in QCD are all gauge invariant operators. Okay. So if you put a double Hilbert space, one of them carrying gauge index, okay, this same situation will happen. Gauge index will cancel out. So that is what is happening here. So if you rotate the GIs, take GI replaced by G prime I, which are also orthonormal, take expectation values of M acting on S. This G prime I will also be, they will cancel out. Right? G prime I, G prime J is delta I J, they will cancel out. So you will get the same answer for expectation values. No observable will be changed. No expectation value will be changed. So that incidentally shows that even here there is a whole unitary worth of purifications even here. correspond to a U2 group, the UN group acting on the G's. I talked about it last time when I talked about entropic ambiguities, and the entropic ambiguity, somebody was asking, comes even though the expectation values are not changed. So the as states, you are not changing it. It turns out that when you compute the entropy, when you have to rotate G, the entropy does change. That and it undergoes a stochastic evolution. This is what I showed last time. I know that I was too fast, but then there was a sparse audience, and my enthusiasm for arguing dissipates. But I was too quick. But that is what happens. And so when you rotate this G, and then compute entropy again using the rules of convex functions, because of a simple application of Jensen's theorem, you find that the entropy increases. After yesterday, I found, in fact, a paper by Raphael again, who uses this kind of technique to argue that the entropy of the black hole will also increase in time. So, let me see. So, suppose now that for some reason,
So this splitting space has pure two-end dimensions. Doubling is necessary and like
n square dimension.
n square. So this doubling is necessary and even for maximum states. Sufficient doubling is sufficient.
You don't have to have to get a representation of the algebra. You don't need these G's.
And for purification.
Purification, you need. I think this is a minimal.
That's what. So 2n is
N squared is minimal, not 2n. N squared is minimal. Yeah, that is my understanding. But again, for infinite dimensions, they twist it with some compact operators and so on. Infinite dimension. So this is the Stein-Spring theorem, which appears to be the granddaddy of all these theorems, which is quite pleasant to read. But I have not found any use for it. Maybe there is something you can do. I'll come back to this equation. I will show this kind of thing happens, for example, in the Riddler. Something is Bala is asking. Yeah, I'll come. So I'll go back. So I have to show that this is cyclic and separating. So how do I show? This is not obvious. This state I wrote down, this is not obvious that if I act by matrices just on the left, I get all vectors of the Hilbert space. This is by no means obvious because there is all this pairing of the indices and what is happening. I want you to remember, even though I have not given the proof. Schmidt, no. I have not thought, maybe. But maybe that there is a route through Schmidt decomposition. But the proof I found is a slightly different technique. So, and also it leads you to this basic theorem of the modular group. Okay. This is a preview. Last few days I found that to take the Riddler wedge. In the Riddler wedge, there is a natural evolution operator, which is given by the boost operator, which is the isometry or the uniformly accelerated particle. It turns out that the algebra in the Riddler wedge is also a local, of the same type as a local algebra. And furthermore, that the evolution operator coming from this modular theory evolves not merely the S, it also evolves the G's. Okay? So if it evolves the G's, the entropy will increase because of the argument I gave. So it appears to be the conclusion that in the Riddler wedge, to follow the path of the accelerating particle, along that path, the entropy will start to go on increasing. It appears to be the case. Does it prove second law? I don't think so, because I can reverse the evolution and still it will increase. So I can't get a direction of time, no matter how much I would like to smudge the thing. I can't get direction of time, but the entropy will increase along these trajectories. What it implies, I don't know.
10% of what?
Hmm?
Yeah. Same percent of what?
Okay, you have this. Yeah, you take a. So in the Riller wedge, you take the vacuum state. So take the Riller observables have a vacuum state, and take the vacuum of the space-time, restrict it to the Riller wedge. Okay. That happens to be cyclic and separated. You can prove that. And the Riller wedge is a globally hyperbolic space. So there is a theorem due to boundaries that if you take this constantly accelerated particles and take a tube around it, no matter how small. So there is a tubular, what is it called? Time-like tube theorem. Okay? So the time-like tube algebra, so it's a tube, it's not a small thickness, okay? No matter how small. The algebra restricted there is this isomorphic, same as algebra in the entire Riller wedge. Okay? Because of the fact that this whole thing is globally hyperbolic, so anything happening elsewhere will go and affect it. Okay? So in this globally hyperbolic space, what is this modular this evolution operator K, which comes from this modular theory or from Unger's calculation? It is a boost acting on the left and minus the boost acting on the right. Okay? Boost operator of say one space and one time is a boost, standard boost acting on the 1, 2, 3. So it involves G. But if it involves G, it is change entropy by general arguments due to people like Jensen. So along this thing, entropy will go on increasing. Okay, does it give direction of time? Alas, I wish it did. Because if I reverse the direction, it will still keep decreasing. But what is true is that it will go on increasing, and presumably the increase of the entropy means that the entanglement between the Riller wedge and the causal complement is getting more and more mixed, I think, because the entropy is somehow a measure of the disorder approaching a classical state.
No, that's definitely not the one.
Huh?
That's only what's happening.
Mm,
Anyway, so you're talking about
thermal entropy.
if you are thinking of like some Minkowski space and split into two Riller wedge, right? Then you have vacuum state on the entire Minkowski space. And you're saying that are you trying to factorize in left and right?
No. There is an entanglement between the left wedge and the right wedge.
Yeah,
Because
so you can't really factorize. But
no.
okay, so then anyway, so your entire story has not answered what is the entropy of.
No, I want it. So
And I mean, if you go back and forth, time evolution, then entropy will decrease.
entropy will go on increase.
It will decrease.
No, it doesn't. No, it's not time evolution. That's the point. The stochastic evolution given by Jensen, you evolve this G by a unitary operator.
No, what I'm trying to say is if you use the stuff that people use, standard stuff that people use, it will decrease. If you're going back to that modular parameter, if you had a EIKS to evolve, where K is like the Hamiltonian, S is your time. If you go back in S, then it will decrease.
That is the point I'm trying to make. The evolution is unitary. No scalar product, no expectation value whatsoever is changed in the activity. For the observables acting on one wedge or acting on the F's. But because of a very peculiar theorem of Kolmogorov and Jensen, the entropy that you are computing using extremal states undergoes a stochastic evolution. So it keeps on increasing whichever way you go. Okay. You know why it happens? I can't.
That's like saying somebody did something peculiar.
This
This is it giving peculiar results.
So see, I am studying before the masters, like Kolmogorov. So I know what to. And Raphael has written a paper. I discovered by talking to my friends that he has written a paper about why the entropy of black hole keeps increasing in time. Okay? And he gives arguments which are close to what I'm getting now. Okay? He is not considering accelerated particles, but he gives what looks like a relative argument. relation argument. Since I have not written any paper, I may be wrong, but I can't find any error yet. Okay. So if my statements survive for one more week, I'll write a paper. Okay.
Going forward, it's at the same place this and backward input, right? The constant acceleration and the backward entropy.
Yeah, my hope was that this will show that the black hole entropy will go on increasing. That's what Raphael shows, okay, by some related arguments. Okay. This I am unable to prove because the unitary group that is here is actually unitary, it's reversible. And I'll write on a formula. Okay. The formula is unitary, so I can evolve backwards. What happens to this Jensen's theorem? It will still increase. Okay. Because Jensen's theorem is on convex sets. It's a general theorem on convex sets. And the whole work of Kolmogorov was in this aspect was to prove that he can model distributive processes using finite sets. Okay. So one of the things he did.
When you look at the entropy of the entropy of the radiation, which is for the paradoxes. When you look at that, you have to look at the system of radiation. And then understand what is its state and then compute its entropy. So, have you done that?
No. I would know how to do it. There is a paper which appeared last week by Bob Wald and collaborators, where they were discussing the coupling of a charge particle in the Kerr-Newman metric. Charge particle, yeah. So, dynamics of a charge particle, mu, electromagnetic field coupled to a charge particle in the background metric. And they computed what happens to start with the pure state for the charge particle background metric, and you evolve in time from minus infinity to plus infinity. They computed the evolution of this pure state, and they found that what was pure becomes mixed. So the title of the paper is how the black hole horizons, even horizons, decohere entanglement. That is the paper, and they estimate time since they say very fast and so on. This is what I do not know, but this is what they have done. So the kind of thing you are telling, others have attempted. It may be relevant here. I don't know. I doubt. So I'll come as you keep going. We keep talking. You'll get familiar to this way of thinking. For example, the G being changed means that you have several purifications giving the same expectation value for the observables. Okay? So you can ask, if I say the entropy of this will change, what about another purification? What happens to it? Okay? Then there is a theorem, there are results which you will find in reviews called the relative modular operator. You do Araki. Okay. Of course, we did it only in infinite dimensions. Okay. He would not bother about finite dimensions. He's a serious person. So he proved. So there is a relative modular operator associated to that. There is a cohomology and there is a calculation of entropy. Whether the entropy I am talking about is the same as the Araki entropy, I don't know. I want to check that. So there, it's not a lonely activity. There is some work already done, which is of physical entropy. I think the increase of this entropy is of physical interest, okay? And the emergence of a gauge symmetry is of physical. Let me say, as a general philosophy, is this entropy thermodynamic? I don't know. Otherwise, if you do it for a thermal state, how do I define it? In any case you do, whether it's a KMS state, thermal, whatever, entropy is always defined intrinsically by decomposing all of them define a state on the algebra. Always. You have to decompose it in pure states and look at the coefficients and use the Shannon equation to compute the entropy. Fundamental entropy is no more than that. So yes, it will apply there also.
Give me a state.
Yeah, it will be a special case. We will see that we'll see later when I go there, that the vacuum restricted to any local algebra is a thermostat. It is actually a KMS state. That is one of the remarkable things these people do. Where the minus beta, what is H? H is in fact the boost operator.
So,
What? If you cannot observe it, then you go home. There is no theory. If you cannot observe things, then your one is playing games. There is no use. It's not physics. Huh?
why is it? So all observations are the same value, but
So that is, I will ask you that question. Entropy is something we calculate from other things, right? So what use is there entropy? I don't know. This is quantum. There is nothing classical in the world.
But it doesn't have to be classic. You can study quantum mechanics with the number of microstates.
So are you saying
This I don't know. See, I don't know how to count microstates coming from this. You may be right. I don't know.
Some framework describes something. This is something to do stuff. But we already have a machinery and it works. And we know entropy is a good. So why would I believe in this and throw it out?
No, I don't. I'm not making propaganda. So you do what you like.
Yeah.
I don't know. To my mind,
I mean, this has to at least satisfy everything that we, and then it can give us something extra.
That would be nice. But the counting of microstates is what I don't know what it means in the quantum field. How degrees of freedom? What does it mean degrees? Let me show you. How do you count? Every Hilbert space is isomorphic to every other Hilbert space. It's a fact. It's a fact. If you take any separable infinite Hilbert space, it is isomorphic to every other separable infinite Hilbert space. What do you do with that? How many degrees of freedom? I don't know.
Look at the energy.
But there is no. Okay. The time evolution is for the entire space time. So you take different Hamiltonians, you get different answers. Now, how do I intrinsically count number of degrees? The statement I am making is that there is no way, but I am saying I don't know how to do this.
I would say that look at the energy that we have of the system and look at the states, orthogonal states near this energy axis. So that nearness is defined by you. The greater the interval, so that's the way classically people do that. They take the energy shell, and near the energy shell there's a thickness, and look at the eigenstates in that energy shell. That will give you the counting. Double entry.
Maybe I don't know. Yeah. To be honest, I don't know what is the physical meaning of entropy. Quantum theory. Classical theory can say I measure.
Counting the state be irrelevant. This is this term grows this different state, then what is it relevant for? Yeah,
There is nothing classical.
From one state to another state. Counting does what I think
I don't know. I don't want to count.
that so log of those numbers is irrelevant as well.
So why should I bother about? To the extent I can understand, I'm willing to change my opinion. If somebody Malayali was here, I will make a quotation from EMS. Opinion is not given stored. I will change my opinion. EMS was it? Abhiprayam irumbu odakiyala. We change. So I don't know. The only thing I can imagine entropy playing a role two is first, it maybe is a measure of the entanglement of your quantum state. Is it pure or is it entangled? So the degree of entanglement, it may be a measure of classicality approaching to its state. It may be. The second thing is the entropy from the mathematics side, has many monotonicity properties. Okay. So these monotonicity properties is used to extract other kinds of results from your quantum system. Okay. So it may be a very powerful tool to do this kind of calculation, and that's what I see people doing. The people who know the mathematics in the control, like Roberto Longo and so on, I find that this is what they are doing. Intermediate things, I am willing to be enlightened, but I don't know how to do it. There is a paper long ago which I have not studied by Schroer and Rudolf Hart, where they give an argument on how to count the degrees of freedom, how to measure the degrees of freedom in any local experiment. That because these people are very thoughtful people, there will be some results there. But as I say, I have not studied this paper. The paper is you can easily access it. One of us can write to the similar place. So let me finish up because it is time. It's also the emergent gauge symmetry.
So I'm saying when the change in entropy definitely does. Change in entropy, you can like response functions and so on. Free energy, and then there will be force and everything. So which is actually useful. So that you don't know, right? I mean, it's not a system model.
And normally, the first point of view I want to take is that world is quantum. There is nothing classical in the world. World is quantum. So normally, what you do with entropy is to define auxiliary quantities from the entropy. For example, from the expectation value of observables, you can make a big table that defines a density matrix or a state. From the state, during the extreme states, I can find an entropy, some number, and it has some nice monotonicity properties. So I may be able to make predictions on what will happen to my measurements. I imagine that this is one of the uses, and maybe if the entropy goes on increasing, you will find that the measurement that numbers will approach some classical distribution, like Boltzmann distribution or something like that, where all the stuff that comes in computing your mixed state are equally. There's an equipartition law which you can check. I think that there may be other. I think there must be some other use, but I don't know what it is.
What I'm saying is that it's change in entropy is see response functions, do something else, what it does, and so that would depend on how the entropies change, right? Through free energy and potentials and so on.
I think. Let me think about. I need. Actually, this is an issue that bothers me, and especially after finding this funny thing about Builder wedge and seeing Raphael's paper. So, what about this gauge symmetry? I just finished off it. We think the gauge symmetry is something very intrinsic. But lo and behold, you go and read Steve Weinberg, his book, volume 1, somewhere you see. And he is treating irreducible representations of the Poincare group for various things. And he shows that for the electromagnetic field, you cannot define an AMU. One cannot intrinsically define a connection at all. FUMU you can define, not AMU. It doesn't exist. So suppose you insist on defining AMU, you have to put in extra degrees of freedom, and that brings in this independent metric in gauge invariance. So from that point of view, this gauge invariance is something that is emerging because we did the wrong thing. We were trying to look for something which was not there from the very beginning. We try to push it in and you find gauge invariance. Is this the case with all gauge invariance? Is it an artifact of our insistence of classical? So why? Well, I don't know whether Maxwell wrote AMU. I think that was brought in by who? I don't know. Probably Poincare. I don't know because I don't know who brought in this connection AMU. Okay? And then all this stuff about gauge theories and connections and very phase effects. I got my promotion by writing a book on gauge transformations. So Now I don't know whether just merited or no. I don't know. Because more and more information is coming that maybe this is an artifact of our mistake. We have to correct it. I don't know. There are too many things we don't know. I think. Okay. I also have strong arguments with Sanathan and so on about Euclidean function integrals and stuff. But, I don't know whether they are reflections of reality. I don't know. Maybe. Okay, I'll stop here because it's 1 hour and 10 minutes. Unless there are questions. I'm completely open to questions, or we can discuss. So I have stopped here, and next time I will show you uh, how to start from this state here, Dumizawa state, and add by some operators in the matrices and generate all the states for the vector space. So this is cyclic state. And I will also show you that the operators coming from the right, which is your conjugate commuting operators, they are also cyclic. So by this theorem I showed you, if it is cyclic both ways, it is separating both ways, and we are done. So I will find that operator, and from that operator, I will show you this Tomita-Tokisaki theorem, which shows that given those things, there is a canonical evolution operator which will evolve this algebra. Okay. This is nowadays called, this corresponds in the Rindler-Wedge case to the boost operator, but the boost operator acting on the left minus the boost operator acting on the right. Okay. So left wedge minus right wedge. This right wedge minus left. This is quite important. Okay. And in fact, it's written emphasizes in this paper on these days. We will show how that emerges, okay, and why I speculate that that will increase the entropy of this state we are writing, because it will also evolve G into something else. So there is a bit of work, small work to do. I'll finish that. Then I will show how to quantize particles of any spin, whatever, without ever talking about quantum field theory, functional integrals, no nothing. One writes down the answer, the full Fock space, and these people have written it down. So we will see how it goes. I think that part is quite beautiful, what they have done. So I'll do that as we progress. Tomita Takesaki is, yes, the whole book, that whole activity, that's why I did this first. Because the Tomita Takesaki, yeah. So, the starting point they start is, look at the algebra and the Rindler wedge. The Rindler wedge happens to be globally hyperbolic. So if you give data on one null hypersurface, okay, as your Cauchy surface, the evolution operator, the standard evolution operator, will evolve this data to the other hyperbolic, to other Rindler wedge. That's other null thing. Okay. So it is a globally hyperbolic space. Okay. And there are arguments immediately that the algebra which is living in this thing is a fundamental algebra of type 3-1. If you take the vacuum and restrict it to this algebra, is fundamental algebra of type 3-1, which I will explain. And that there is this group acting on this, which happens to be exactly the Unruh boost operator, which we use all the time for constantly accelerating the particle. It comes out. You don't have to do anything, it comes out. And it is a thermal state. That also is a subsidiary thing, which you can show using the Tomita Takesaki theory. Yeah. Then comes the fact that you have, in their approach, there is Poincare invariance, in particular Lorentz invariance. So you take this little wedge and start translating it by Lorentz. So one Rindler goes to another Rindler. Okay. They all have the same property, except that the boost operator changes. Okay. So you told me this paper of Bosch's.
It's the other way. Concrete book is not an input based on output of the outside.
I read Okay, but let me. So they take this little wedge, then they start intersecting. Then you, for example, the causal diamond and all those things come intersect. So you go on taking all possible intersections. They all have the same property. Okay? So you get an infinite net. Actually, what you are getting is directly infinite net. So you have an infinite net of these local algebras. Okay? Each of them carry their own k. For Riddler wedge is a boost. What is it for the causal diamond? We only know it exists. These are local algebras. So there is a local automorphism acting on these algebras in every one of those things. Okay? This is known. Do we know what those operators are? No. Okay? Except for if you are conforming various, Roberto Longo has computed it by conformally transforming the Riddler wedge to causal diamond. It is a long quite a difficult calculation. It's just done. We have to check all kinds of factors. Generally, answer is not known. So, using this, these fellows are able to prove how to write a quantum field, a Fock space completely in this whole net. Okay? They don't emphasize it, but we can see that in this calculation, some local algebra, some local symmetries are emerging. Because you have, for each wedge, you have a boost operator that acts only on that algebra, and it is an isometry of that algebra. Go somewhere else, some other boost algebra. What happens if you take intersection? What is a boost algebra? How do this interlace? I don't know. My suspicion is that if you do this, you will see that the Poincare group emerges. Like the Kappa theory may emerge. I don't know. I think Marcus is going in that direction. He's translating this wedge by translations. So to translate it, the intersection or rotate. So for example, take one rotating bit in the intersection region. There is one boost from one wedge and another boost from another wedge. Okay, or maybe rotate in some other way. Then presumably the commutator of the two boosts should also be a symmetry, but that will create angular momentum, rotations. Will they fill up the full Poincare group? I don't know. I think that Poincare group will be emergent from this local length. And space-time will emerge purely from the topology of space-time. I think so. But how? I think that will be, that's a problem for you, your thesis. You'll become celebrated. Okay. Any more? Okay. So continue with this next one.